Given the curve y equals x squared on the interval from 0 to 3, construct a solid by revolving that curve about the x-axis and find the surface area of that solid. So let's take a look at our picture. What will that look like? Looks like this from 0 to 3. We're wrapping it around the x-axis. So can you visualize it? What's it going to look like? Something like this. You see it? Got a couple other options here for you to get a feel for what they look like. Here's another possibility, right? Taking y equals x squared, wrapping it around from 0 to 3, or another possibility in terms of what it looks like. We want to determine the surface area of this. And this is based on what? This is based on decomposing the graph into smaller pieces and wrapping each piece around. And each piece that I wrap around is what? Is a frustum. So we take a look at this frustum right here, for example. Okay. We want to figure out what that surface area is of that frustum. And we're going to add all of those together. So let's think about how this is going to work. So again, y equals x squared. Just going to pick something here. We have to envision that as a frustum. And then, of course, it comes down on the other side. We draw a straight line here to make that frustum. Maybe it's more like this. And this is my smaller radius, and this is my bigger radius. But what I'm going to put in the middle is something called x. And you'll notice that f of x is here on the graph, right? There's f of x, and f of x is between the smaller radius and the larger radius. So our average radius in this case is again going to be f of x, which is x squared. Because in essence, we're going to keep making these partitions smaller and smaller and smaller and smaller. So big R and little r essentially come together and are essentially the same value and are f of x, as we can imagine this. Now, what else do we need? We need the arc length. The arc length, L, is the integral from something to something of the square root of 1 plus dy dx squared dx. We've proven that on an earlier video. So in our case, again, y equals x squared. So dy dx is 2x. So what do I get for my arc length? I get the integral from something to something of the square root of 1 plus 2x squared dx. So where does that put me then for my surface area? Surface area of a frustum is 2 pi L times the average radius. So we have L, we have the radius, we can go ahead and do this. And we're integrating this from 0 to 3. So the surface area of the frustum will be the integral from 0 to 3 of 2 pi. The L part is going to be the square root of 1 plus 4x squared dx, because 2x quantity squared is 4x squared. I'm going to hold off on the dx until the end. And then what do I have? Then I have my r. What is my r? My r is f of x. My average r is f of x, which is x squared. And this is not an integral that I want to try to solve. I don't see necessarily an easy way to do it. Maybe we can play with things like trig substitution to get somewhere, but let's jump to technology and see what technology gives us. So going to Wolfram Alpha, I want to integrate two pi times the square root of 1 plus 4x squared times x squared dx as x ranges from 0 to 3. What do we get here? Do we get a nice answer? We get an answer working with the inverse hyperbolic sine. So my guess is with enough muscle, we could probably get this to work with trigonometric substitution. But that's not really the point of this lesson. So let's go ahead and just take our approximate answer here of 261.32. And that would be measured in square units. So that's the surface area of that frustum that we're working off of. And remember what that thing looked like. Something like this. So we have 261.32 square units to find that. That's when we wrap the thing around the x-axis. But now let's try to wrap it around the y-axis. So the same thing, y equals x squared on the interval from 0 to 3. Let's wrap that around the y-axis this time. And that's a little easier to visualize. So this time we're going to say, given the curve y equals x squared on the interval from 0 to 3, construct a solid by revolving the curve around the y-axis. And then our goal is to be what? To find the surface area of that solid. So what does that look like? A little easier to visualize. We have our parabola here. We wrap it around the y-axis. It's going to look like this. And we have a bowl. And we're going to want to have the what? We're going to want to have the surface area of that bowl. So again, we're going to break this into a whole bunch of pieces. We're going to create frustums. We're going to figure out what the surface area of each of those individual frustums are going to be. So looking at our picture, we're going to call this X. And we need to do what? We need to get the arc length. So we know what our arc length formula is, right? Arc length is the integral from a to b of the square root of 1 plus dy dx squared dx. We know that. So knowing that, the arc length portion will be what? Dy dx is 2x, so dy dx squared is 4x squared again. So my arc length is still going to be integral from a to b of the square root of 1 plus 4x squared dx. We'll figure out our endpoints later. Now, for our surface area of the frustum, remember these are a bunch of frustums that we're going to stack together. The formula was 2 pi L average radius. Well, we have L, we need to figure out what the average radius is. And this one is kind of interesting. This one is kind of interesting because the radius here is not f of x. The radius here, distance from the center to the curve, is x. Do we see that? So this part here, little r is a little bit less than x. Big R is a little bit more than x. So remember, our r with a tilde is the average of the two radii. So that's the big radius plus the little radius over 2 for our frustum. Our frustum, right, looks like this. Little radius upstairs, big radius downstairs. So r tilde is the big radius plus the little radius over 2. Again, my big radius is this one, a little bit more than x. My little radius is this one, a little bit less than x. But their average will be x, or very, very close to x. And as we make smaller and smaller and smaller partitions, the big radius and the little radius are basically the same. So they're both basically going to be what? Both basically going to be x. So in this case, my radius, my average radius, is just x. So we know that. So that's helpful for me. 2 pi LR. So putting this together, then where are we? Surface area. My integral ranges from 0 to 3 as I stack all these together. 2 pi. The L part, square root of 1 plus 4x squared. The average radius, again, that's the challenging part of this exercise. The average radius is just x, from the axis of rotation out to this value x. Average radius is just x. And what do we finish with? We finish with dx. And this is one that I actually can do by hand, so I guess I probably should. Let's do a u substitution. U equals 1 plus 4x squared. Du dx is 8x. Du divided by 8x is dx. If x is 0, what is u? 4 times 0 squared is 0 plus 1, u is 1. If, let's see, if x is 3, 3 squared is 9, 9 times 4 is 36, plus 1 is 37. So u goes from 1 to 37. Then we get 2 pi square root of u times x, and then dx is du over 8x. So we're happy that the x's go away. X's divide out. 2 pi over 8 comes in front as pi over 4. Then I have the integral as u goes from 1 to 37. Of what? Of square root of u du. Surface area is pi over 4. Times the integral as u goes from 1 to 37. U to the 1/2 du. Antiderivative of u to the 1/2, u to the 3/2 over 3/2. Surface area is pi over 4 times u to the 3/2 over 3/2 as u ranges from 1 to 37. Does that give me surface area is pi over 4 times 2 over 3. Dividing by 3/2 is the same as multiplying by 2/3 times u to the 3/2 as u goes from 1 to 37, which is 2/12 of pi or 1/6 of pi or pi over 6. 37 to the 3/2 minus 1 to the 3/2. Or 37 root 33. 37 times the square root of 37. That's what I should have said. And we get that answer. And as tedious as that was, let's do a quick check on technology to see if that's correct. I'm going to feed Wolfram alpha my original integral, which is here, 0 to 3 of 2 pi times the square root of 1 plus 4x squared times x to see if I get that result. So let's go to Wolfram alpha, which is here, and I'm integrating what? Integrating 2 pi times the square root of 1 plus 4x squared times x dx. The x squared was a much more challenging integral. Do we get the answer that we expect to get? So 37 root 37, that of course is 37 to the 3/2 minus 1 times 1/6 with a pi. That looks good to me, so we'll call that correct.